All right, chapter 14 is what we call unit circles. Can I get a show of hands who heard or seen the unit circle before? Okay, that's pretty good. All right, well then, that could be quicker to teach. All right, let's go. Unit circle, we're saying that if we have 1 unit length in either direction, we get this nice perfect circle on a Cartesian plane, which means x and y axes. We know that with that simple idea, if it's unit length, then to find the circumference, which means the distance around the circle, what's the formula for the circumference again? It's pi times diameter or 2 pi radius. Very good. So 2 times your radius and then times pi. But since the radius of this unit circle is 1, because we're talking about a unit length, and it could be 1 centimeter, 1 millimeter, it doesn't matter, 1 of anything, right? So 1 unit length, then that means the distance of this unit circle, or any unit circle, should then be 2 times 1 times pi, which ends up being 2 pi. Okay, so the basic idea is that 1 revolution in any full perfect circle should have a distance of 2 pi. That's the idea. All right. Obviously, if it's more than 1 unit, then it's just a dilation. You just stretch it. But we're just saying 1 unit of any perfect circle should have a full revolution of 2 pi distance. Now, with that in mind, one of the other things we also know in terms of angles is that if you did rotate, so to make that distance of 2 pi, I need to have a full revolution of 360 degrees. So what we can sort of relate to is that the angle and the distance are proportional to each other. So if that's true, well then we can say 360 degrees is equivalent to, so this is an angle measurement versus a distance measurement. Okay, one is measuring the distance around the circle, one is just measuring the angle that it rotates. 2 very different measurements. Okay, so we call this radians, which is essentially the measure of the arc. Okay, that's like your circumference. It's the portion of your circumference. This is the degrees that you're used to, but that's the rotation. Okay, 2 different things. But obviously they're interlinked. So if you went 45 degrees, then you would have gone a certain portion of the distance of a circle based on the angle. So your first exercise 14a has 2 formulas for you to either memorize, or if you understand that fact that I just described, that 360 is equivalent to 2 pi, you can actually derive the formula yourself. And that way you don't have to memorize it. Okay? So here's an example. Let's say I wanted to convert degrees to radians. Okay, let's say the question was, what is 30 degrees as radians? Right? Let's say that's the question in exercise 14a. Well then, with this same concept, I can actually, if I want 30, I can work out how many 30s fit in 360. But if it was a number that doesn't fit in 360, the best one is to work out, well, how much is it for 1? Because if you know how much it is, how many radians there are for 1 degree, then you can work out for any degree, right? So the logic here is, well, if I got 360 of these degrees and I just want 1 of them, well, then the logic is I divide 360 by 360, that will give you 1 degree. But since they're equivalent, whatever you do to one side, you must do to the other. So if you do to the other, dividing 2 pi by 360, you can already see 2 pi over 360. What can you simplify already? Yeah, the 2 and 360. So that becomes 1 and 180. So this formula, as you can see here, now becomes pi over 180. You might be thinking, well, how is that a formula? Well, if you know that's for 1 degree, 1 degree is equivalent to pi and 180. And if I have 30 degrees, I have 30 of them. So how would you work out 30 degrees? It literally is 30 degrees. I want 30 of those. So if I want 30 of those, I need to times it by that by 30 times. So you times that by 30. And that's the formula that they normally tell you in your textbooks. They'll say to go from degrees to radians, times by pi and 180. Okay, so times by pi 180. So if you didn't understand how I got to that formula there, you can write this down and just memorize it. But that's what I'm saying. That's 14a. 14a is to memorize how to go from degrees to radians. And I just followed the logic. I got 1. So if I want 30 of them, times it by 30. So 30 and 180 cancels out to be 1 and 6. So that's what radians is. I've moved pi over 6 distance when I make a 30-degree angle. So if I draw it out, say this is a 0-degree line, 30 degrees is about here. When I make 30 degrees, I've moved a distance of pi and 6. Because remember, it was 2 pi, which is like double of 3.14 something. That's the distance outside for 1 revolution. So if I did 30 degrees, I've done pi and 6. So 3.14 divided by 6. Whatever that is, that's the distance I've covered. Okay? So that's called radians versus degrees. Then you can do the same for the second one. Well, what if I wanted to do radians to degrees? Okay, so what if I wanted to convert 3 pi? Now we can probably figure out what 3 pi is just logically, since we already know 2 pi is 1 full revolution, so that's 360 degrees. And if I did another half revolution, that's an extra pi. True, because it takes 2 semicircles to make 2 pi, so another semicircle must be 1 pi. Right, so that's together is 3 pi there. So what's the revolution in angles? It's 360 plus 180, and that should be the angle. But instead of using some sort of logic, I'm now asking you, what's the formula for it? Okay, so what's 3 pi in terms of degrees? Well, this is what we can do. We can do the same thing again. This time, I just want to know 1 radians. Okay, so 2 pi radians equals 360. To get to 1, I need to divide by 2 pi. 2 pi divided by 2 pi gives you 1 of those radians. But then, if you divide the right side by 2 pi, you divide the left side by 2 pi. And conveniently, you get something similar. 360 divided by 2 pi simplifies down to 180 on pi. So this is your second formula that your textbook will either ask you to memorize, that if you want to convert radians to degrees, you just simply times by 180 on pi. Okay, so that's the reverse. So in that case, since 1 radians is equal to 180 on pi, if I want 3 pi of them, I need to times this by 3 pi. So to work it out, it's 3 pi times 180 on pi. Conveniently, the pi's cancel out. Pi divided by pi cancels out. 3 times 180, 540. So if I had to tell you what is it in degrees, when you say 3 pi radians, the distance you've covered, okay, that's equivalent to you rotating 540 degrees. Okay, so you did 1 revolution and then another half revolution. That's what 540 degrees is. So if I zoom out, that's exercise 14a. Okay, 14a, something to take away is just 2 formulas, how to convert degrees to radians, radians to degrees, but to understand the difference between the two. Okay, and that comes from just looking at the unit circle. Yeah, some basic Year 8 mathematics, understanding what a unit circle is, comes down to 2 formulas for 14a. So it's conversion. Yeah? All right, so here I did this one for you before. So 30 times pi on 6. Oh, sorry, not pi on 6. It was pi on 180. And that turned out to be pi on 6. And you can work this out for yourself as well. Okay? All right. Second part of the theory, which arguably is the basis for chapter 14. Those who learnt unit circles have seen them before, so hopefully you were taught this unit circle idea. So I'm just going to go through some of the basics here. Starting from the x-axis. Conventionally, that's where 0 degrees is. Okay, that's where you begin with your protractor. That's 0. And we rotate anti-clockwise. Okay, so that's the first thing to remember. 0 degrees starts here on the x-axis, and we go anti-clockwise. So when you say 30 degrees, we always go anti-clockwise. We don't go clockwise. Notice that when you go anti-clockwise, it's positive. Angle's positive. If you go clockwise, the angle will be negative. So if I said negative 30 degrees, what we're saying is we're going clockwise 30 degrees. If I'm saying 30 degrees positive, then it means I'm going anti-clockwise 30 degrees. Okay? So that means when you draw your axes, it splits up the circle into 4 pieces. We call them quadrant 1, quadrant 2, quadrant 3, quadrant 4, and it's in that order because we move anti-clockwise. Okay, so we go anti-clockwise as 1, 2, 3, 4. So next time when I ask you which quadrant is the angle in, you should either tell me Q1, Q2, Q3, Q4. Right? Now let's look at some basic ideas. If this is a Cartesian plane, then when I rotate a certain angle, okay, say 30 degrees for example, I would have reached this point on the XY axis. Now that point has a coordinate. It must have an X and a Y coordinate. True? So that point there has an X length and then it's also got a Y length. What's convenient is that point is on a circle, but when you draw it out, can you see I get an X length, which is here, and I get a Y length, which is here. Isn't that just a right-angled triangle? Because that has to be a vertical length, horizontal length, so it must be 90 degrees. You get a 90-degree triangle, and this is the angle you rotated. This represents X, this represents Y. And back in year 9, with right-angled triangles, there's only 2 techniques that you've learnt so far. What 2 techniques have you learnt in year 9 that deals with right-angled triangles? What's the first one? Pythagoras is one of them. Okay, so likely one of the identities in trig is a Pythag formula. So you got a Pythagoras. What's the second one? Yeah, trigonometry, which is trig ratios. So SOHCAHTOA. Right, so there's only 2 techniques. One, Pythag. When you think of right angle triangles, you have to think about Pythag. Or 2, SOHCAHTOA. Those are the only 2. SOHCAHTOA, let's see where this comes from, or the idea. See, when we say SOHCAHTOA, we're saying this hypotenuse. Notice, what is the hypotenuse? We said it was a unit circle. So that's radius 1. When you draw that, that's also the radius. So the hypotenuse is already 1. But if I asked you to find sine and cosine, see, sine of the angle is equal to opposite over hypotenuse. What's my opposite in this case? What's my opposite? The y. So I got y over hypotenuse, which is 1. And it turns out y divided by 1 is just y. And you end up with sine theta. So this is why we say when you type on your calculator sine of 40 degrees, sine of 30 degrees, whatever answer that comes out, it's actually just telling you the y coordinate as you're moving around the circle. Okay, so wherever you are in the circle, when you type an angle in, and whatever sine of that angle is, it actually just represents the y value. So over here, can you please write y equals sine of theta? Okay, so this is your y coordinate. And here's an example of what I mean. So I'm going to use a CAS calculator to illustrate my point. Back then in year 9, when you type things like sine, so go to the trig side, and you do sine, whoops, I got to delete that too. Sine, yeah. What's going on? Sine, and just making sure you're in degrees. I'm going to change that to degrees. When you say sine of 30, for example, which I know is half, but back then what that's trying to say to you is that when you draw a circle, not even a circle, if you had a unit circle where you moved an angle of 30 degrees and a unit of 1, they're just saying this point, that coordinate there, you just found out the y value is half. That's it. That's all you're really saying, because the sine value is that height. Okay? And we know that in a unit circle, the max height is 1. because it goes radius 1, radius 1, radius 1, radius 1, radius 1. So the max height you can get is 1. This is why every sine value that you did can only be between -1 and 1. That's why in Year 9, you might have, if you did the enrichment questions, they might have asked you something like this. If you tried to find the inverse, and they say find the inverse, you can find inverse of any number between -1 and 1. But why wasn't it possible if you had more than 1? So for example, I put 2, it's undefined. And the reason why is because we just saw a unit circle can only have a max 1 or a minimum 1. So when you say what angle can you type a sine in so that you have a y value more than 1, which is 2, it's impossible. Because your unit circle, the circle has always been defined by what we just said. The sine, the ratio of this versus 1, it's always dividing by 1. Max length is 1. Okay, so that's why when you do sine inverse, if you're looking at your calculations and you see a number that's bigger than 1, it's not going to work. You've done something wrong. Yeah, because mathematically, we're saying unit length of 1, this is the y value, so the max y value can only be 1. So there's no angle that you can come up with that will give you a value bigger than 1. Yeah, so as you're moving around the circle, the y values change. So at the beginning, at 0 degrees, y value is 0. As you increase, the y value increases. So the y value gets larger, larger, larger. So by the time you get to 90 degrees, sine of 90 should be the max height. So hence it's 1. So even without doing any calculations, I'm just looking at that unit circle picture. I can already tell you sine of 90 degrees. Whoops. If I go back here and I type sine of 90 degrees, it's 1. See, that's not me memorizing it, just me reading the unit circle. You see, if I ask the same question again, sine of what angle to make sure that the y value is -1? What's the angle to make sure my y value is -1? What would the angle have to be? Look at the circle. So what would I type in the calculator? Sine of what angle will make sure the y value is going to be -1? Let's try 180. Here we go. So I get a 180. Sine 180. I get 0, not -1. Now why is that? So let's have a look at what Anthony just said. Where is 180 degrees? 180, this is where 0 is. 180 is half a circle. That's 180. So you end up here. You see that? That's 180. So if I ask you, rotate 180 degrees, this is 90 degrees. Here's another 90. So you end up there. If you end up here, if I ask you, what's the coordinate at this spot? You would say it's -1 and the y value is 0. But I'm asking, what if I want the y value to be -1? Not the x value. I want the y value to be -1. 270. Let's try it. Sine 270. See that? Because in order to get that, all I'm doing is I'm just rotating. See, that's 90 degrees, 180, y value 0. If you just look at the y-axis, at that point, what is the y value? 0. At this point, I don't know what the y value is, I just know it's negative, because it's below the x-axis. And then, by the time I reach here, that's the maximum length I can get. So it has to be -1. So sine of 270 is -1. But that's all it's saying. Sine just tells you the y values, and cos just tells you the x values. Where's cos? Cos, if you look at this, cos is adjacent divided by 1. You say it's x over 1. That's why in your notes, I want you to fill in this side. That should now be cos of any angle, essentially tells you x. Yeah. Sine of -9. Yeah, you can. And what does that mean? So let's picture it. Negative angle means that you're going clockwise now. So positive values go anti-clockwise. So if you picture it, this is where 0 degrees is. If you want to rotate -90 degrees, you're rotating this way. Now if you rotate -90 degrees, you'll end up here. Now if you think about the x and y axes, maximum length of 1. By the time you get to -90 degrees, this is a maximum length of -1 vertically. So the coordinates would be 0, -1. So if I asked you before, if I want -1, it didn't have to be sine of 270. It could also be sine of -90. Same thing. Okay, so it is literally the angle that you come up with is just rotating you into a certain quadrant. There's only 4 quadrants. There's only 4 positions you can end up in this circle. And the angles just tells you where it is. So why do you work in degrees and not, work in radians and not degrees? It's because degrees gets confusing. You only know up to 360. But if I said 1,806, I'll be like, which quadrant am I in? That's much harder to figure out, right? But radians, why do we like radians? Well, there's a pattern to radians. So if you think about the radians version, you start off with 0. You told me that a full circle was 2 pi, right? But then halfway must be half of that. So halfway, which is, if I went from here to here, that should only be pi, because that's half the distance, right? Full distance 2 pi, so half the distance must be pi. But the beautiful thing is every semicircle is a pi. So if that's true, well then, this is pi, 2 pi, and if I did another half circle, that's now 3 pi. If I do another half circle, 4 pi. If I do another half circle, 5 pi. If I do another half circle, 6 pi. But what's the pattern? 2 pi, 4 pi, 6 pi, pi, 3 pi, 5 pi. What's the pattern on either end? What are you seeing? What makes it so special? Anyone notice the pattern? So if I said 99 pi, where would 99 pi be? Yeah. This is the odd numbers and these are the even numbers. So that's why in radians we like working, because as long as you know whether it's odd or even, you can work out where you're starting from. And so if I said 22 pi on 6, let's see if anyone can figure this one out. 22 pi on 6. See, if we worked out the degrees for that, that's pretty huge. But you can probably work out roughly where this is. So let's simplify 22 pi on 6. That gives you 11 pi on 3. Now, we like working in whole numbers. So how many 3's fit into 11? Roughly. How many 3's fit into 11? 3, right? So we already know 3 pi is somewhere over here. But the problem is that I can actually get closer. I can get closer to a whole number. What number divided by 3 will make it a whole number? What number do I need? Because that's 11 right now. So you told me I can either have 9 divided by 3, which works, but I'm sitting at 11. The next number is 12. Now, which one's closer? 9 over 3 or 12 over 3? Which one's closer? 12. But if you divide them, 9 divided by 3 gives you 3 pi. 12 divided by 3 gives you 4 pi. So when I ask you, where's 11 pi on 3, it's clearly going to be closer to 4 pi than it is 3 pi. Because 3 pi is over here, 4 pi is over there. If I said it's closer to 4 pi, it must be somewhere in quadrant 4. See the logic? Now we actually have to work out what 22 pi on 6 is as a degrees. Using your formula that you learnt just now, you would have done 22 pi on 6 times by, 180 on pi. See, if I asked you before where 660 degrees is, some of you might be able to work it out. But the larger the number, the harder it is. If I went to 99 pi on 3, 99 pi on 6, I've asked you where that is. See, it's harder when you're working in degrees, but radians is better. So one of the challenges in this chapter, why do students struggle with understanding unit circles? Part of it is fractions. Part of it is that you don't know how to work out your holes. You don't actually understand where the unit circle is, where you're at. See, when I asked you at 22 pi and 6, a lot of you might be like, whoa, what is that? But then when I asked you, how close is it to a certain pi? Why am I asking how many holes? Because I'm looking for which direction you are in. Knowing 9 divided by 3 was 3 pi, great, it's over here. 12 divided by 3 was 4 pi, so 11 pi must be closer to 4 pi, so it has to be here. Quadrant 4. Does that make sense? That's part of the skills that you're going to learn in 14B, 14C. This is what you need to work out. The first skill is to know which quadrant you're in. Because if you know which quadrant you're in, you can then tell me, is it the X value positive? Is the Y value positive or negative? You'd then be able to figure it out. Okay, because the whole point of the exercise is to know, do you have an X coordinate that's negative? Do you have a Y coordinate that's positive or negative? That's what you're working out for. Okay, so let's look at the last one. So we talked about X and Y's. I gave you a bit of an intro to symmetry properties there just now. Last one is tan. Do you guys remember what tan, the ratio was? So sine was opposite of a hypotenuse. Cos is adjacent of a hypotenuse. Then what's tan? Whoa. Opposite of adjacent. Now let's look at that triangle again. If this was theta, this is Y, this is X. Which one's my opposite again? Y. Which one's my adjacent? X. But according to what you just wrote, over A, isn't that the same as writing Y over X? Well, what's Y over X? You've seen that before. How much you rise, cross how much you run. Gradient. This is one of the first formulas I gave to you at the very start of the year when we did chapter 1 and 2. I told you that tan of theta was equal to m. That was one of the properties that you learned in chapter 2. Most students forget that because it's not about memorizing, it's about understanding what it represents. See, tan theta was opposite over adjacent, and as I'm drawing the triangles, now you can see why tan of theta is the gradient, because you're just measuring how far you go across and how far you go up. It tells you the steepness of a line. That's all it does. It just tells you how steep a particular line is. So let's remind ourselves, what are the 4 types of gradients that you have again? You've got this line, which is called the positive, this line, and this line. Give me the names. What's this one called again? Negative. So this is the negative gradient. What's this one called? 0. And the last one is? Undefined. Very good. Now let's test your understanding so far. Can you see in that unit circle picture, if tan represents the gradient, which is the slopeness of the line that you create, when you create an angle, starting off at 0, every time you rotate, the line actually changes steepness. See that? That's steepness. Now, just logically, can you see that to get a vertical line, what angle must I have? So if I want undefined, if I want this line, see that rotation? I'm rotating it. If I want that line, well, what angle do I have to rotate to get an undefined line? 90. Let's try it. So if I go to my calculator and you type in tan 90, it's undefined. See, that's what tan means. Tan is just talking about the rotation. What if I want the angle to be negative? So right now, so not the angle negative, I want the gradient to be negative. See, this is a negative line. You told me that's the negative line. What angles will make sure that you have a negative line? Give me a number. Tan of what? 91. Let's try that. As long as it's bigger than 90, right? So if I go to now tan of 91, tan 91, it's negative. So because you're now understanding unit circle, not memorizing it. You're understanding to read the unit circle. But it doesn't have to be in quadrant 2. You see, when I rotate, by the time I get to quadrant 4, that's also a negative gradient. So you can choose any angle that is larger than 270 but less than 360, and it'll still be negative. So if you chose, I don't know, 300. So if you did tan of 300, it's also negative. Because all it tells you, tan is just the gradient, cos is the x coordinate, and sine is the y coordinate. If you just get that, that's the fundamental parts of unit circle to begin with. Okay, just that bit. And the rest is now symmetry properties. So you're just trying to figure out where you are in the set. So far, so good? Okay, so in your notes, you should have now a bit of an understanding of cos when you type it in your calculator, sine, what it is on your calculator, and tan on your calculator. Today's lesson, and just to finish it off, I know it's a big lesson, there's 3 exercises, but the key takeaway was degree radians conversion. Second one was this bit, sine cos tan. Yeah? What does sine cos tan mean? Let's now, have you guys heard, I'm not sure when you first learned unit circle, did you guys learn ASTC? Can I get a show of hands who've seen that before? 1, 2, 3. And show of hands who have no idea what ASTC means. Okay, cool. So, ASTC is an acronym, which I don't like teaching, but a lot of students do it. ASTC is an acronym for all scientists, this could help you, tests chemicals. Or I think my accelerator group was like, what was it called? Something silly trans club. I forgot what A stands for, but they made up their own acronym for it. But what's the ASTC? Okay. A represents that the x coordinate, the y coordinate, and the gradient is all positive. That's what A stands for, all positive. Now, I want you to think about it, not even just in ASTC form, whether that's true or not. Can you see when I draw an angle, this coordinate in this quadrant, quadrant 1, doesn't it make sense already that x is positive, y is clearly positive to be over here, and clearly looking at the line, gradient's positive. If I use that same logic with you, let's rotate it over here now. What if I had a point on this side? So in quadrant 2, what can you tell me already? What's my x coordinate? What's my y coordinate? And what's my gradient? Is my x positive or negative on this side? Negative, right? So on this side it's negative. Is my y value negative or positive on this side? Positive. Is my gradient positive or negative on this side? So look at the gradient. Is that positive or negative? Negative. Very good. But can you see, out of all of them, which one's positive? It's y. And what did we say y represents? Sine. So this ASTC, for those who've never seen it before, it actually just means this region's where sine's positive. This region's where tan's positive. This region's where cos is positive. But you don't have to remember ASTC, because if you just look at the quadrants, if you just look at this region, it's so obvious. X, Y, M. X is clearly negative. Y is clearly negative. And the gradient is positive. That's the only thing that you can see there. X is negative, Y is negative, and the gradient's clearly positive. You don't have to memorize that. You don't need to memorize ASTC, because you're just literally reading the coordinates in each position. Every coordinate. At that point, X is positive, Y is positive. Over here, X is negative, but Y is positive. And over here, both X and Y is negative. And the gradient's positive. And then same thing with the last quadrant. So this one is X is negative, Y is negative, tan is positive. And over here, X, Y, M, and you can see again, X is positive, Y is negative, and gradient's negative. That's why they say cos, which represents your X coordinates, is positive. That's the cosine region, all regions, sine region, tan region. But you don't need to memorize ASTC, because you're just reading the unit circle. Because the whole point is to know, is X positive or negative? Is Y positive or negative in that region? And that's it. And your gradient, is it positive or negative? And you guys did that way before I taught you ASTC, because you already know how to read a Cartesian plane. The ASTC are for those students who have no idea what unit circle is. That's why they memorize that. Okay, but you don't need to. You're just reading the quadrants just based on the coordinates. Yeah? All right. Now, why is this useful? Let's do the first one over here. We're going to do this example. And then I'll leave you to just digest the information from here. But this is pretty much what you want to practice. This is like your times tables. If you don't get this bit, then the rest will be pretty hard for chapter 14. So you're going to learn, like your quadratics, you must learn how to solve these kind of problems. So I'm going to guide you through them. Here we go. Cos. Let's start off. Ooh. Let's continue the video. All right. Let's start off. Unit circle. So the whole point is understanding unit circle. Cos. What does cos represent again? X, Y, or gradient? Which one is it representing? Cos. Cos is your X. So we know I'm focusing just on the X. So I want you to picture when you do this, you draw a unit circle in your head, or you can draw it on paper, and you ask yourself, okay, so I want X coordinates. What I don't know is it positive or is it negative? Because at the end of the day, if you type that in a calculator, it's going to be positive or negative. True? So you just need to figure out, is it positive or negative? Don't even need ASTC for this. So the problem is, X could be positive or negative. I just don't know which region. So your skill today is to learn how to read the region. 5 pi on 6, that's in radians, not in degrees, right? But radians is better for you to read. So this is where your fraction skills come in. 5 pi on 6 is here. This is what you want. Now it's out of 6s. So you can go through your 6 times tables. Is it closer to 0 divided by 6 or is it closer to 6 over 6? Closer to 6 over 6. Now 6 over 6 is equal to 1 pi. So where is 1 pi on this circle? Where's 1 pi? So remember the full circle is 2 pi, so 1 pi must be? Very good, it's over here. Okay, so 180 degrees. So I'm moving over here, but remember I'm short of 1 pi. Yeah, I'm less than that. I'm closer to the 1 pi, but I'm less than that. So if I'm less than that, I must be in quadrant. What quadrant is this called? Quadrant 2. So I know, just from this logic, already, I am somewhere in this quadrant, quadrant 2. To be more exact, if this is where 6 pi on 6 is, which is 1 pi, that means I'm only less by pi and 6. This region here must be 5 pi and 6. True? Because if this is 5 of those pi's and 6, then this is the leftover 1 pi and 6. This is where your fraction skills come in. Alright, so when I say what is cos of 5 pi and 6, I'm just asking at that particular point, at this coordinate, I'm asking what is the x value? That's what it's asking. See, 5 pi and 6 is this side. The leftover is pi and 6 to make up that 6 pi. I know I'm over here. Quadrant 2. And all you're asking now, is this a negative answer or is it a positive answer without using ASTC? Look at the x coordinate. Is that negative or positive? It's negative. That's it. That's all you're doing today. Today, you're practicing to understand the answer is a negative. But you see this triangle that I've drawn? This is 5 pi and 6. That's an obtuse angle. We usually like to work with acute angles. Okay? Because acute angles gets you that right angle triangle there. So what angle or what degree or distance is this? If this is 5 pi and 6, this leftover must be pi on 6. So if I drew out that triangle, we know this is pi on 6. Well, it's not really the angle, but it's in radians. That's pi on 6 here. It's 90 degrees here. And you're trying to work out for this, and the hypotenuse is 1. So, if I want to know that distance, that is the same thing as saying cos of pi and 6. True? Because cos of pi and 6, remember, cos of pi and 6 should equal to adjacent over hypotenuse. Adjacent over hypotenuse, but that equals to x over 1. So x must equal to cos of pi and 6. This is all they want you to do for the first, or B and C. B and C is getting you to understand this bit. That when you type on your calculator cos of 5 pi and 6, that's an obtuse angle. This is the acute angle. But they're both equivalent. They want you to see the equivalence because there's multiple ways of working around the circle to get that point. Okay, so you could have done another full revolution to get there as well, but they're trying to use what you currently know. Okay, so watch, when I type on my calculator, if I go to cos of pi, 5 pi on 6, and yes, you can actually type pi in your calculator for that too. I'm going to change it to radians again, so change the mode to radians. And that gives you negative 0.866, right? But watch what happens when I type in negative. Negative. Negative of cos of pi on 6. It's the same answer. Okay, so your skill today is to work out, instead of an obtuse angle, what if I want an acute angle? Usually they might even give you which quadrant domain. So they might say the angle is between 90 and 180. They might say the angle is from 180 to 270. You just got to figure out what angles it is or where it is in. Start off with. Okay, so copy that example just to get a feel. Later on you can do it without even drawing the diagram. Let's do another one. Let's do this one. Sine of 23 pi on 6. That's my last example for today. Okay, because it's been on for quite a bit actually. Here we go. Same thing. Sine. What values am I looking at? X, Y, or gradient? Which one is it? Y. So I'm looking at the Y coordinates. The only thing I need to figure out is it positive or is it negative? That's it. There's only one question there. Yeah, so unit circle again. Here we go. Your problem is 23 pi and 6. So go through your fraction skills. And it's out of 6s. So you got to go through your 6 times tables. 23 pi and 6. What's the two closest value? What's the one before and one after? We got 24 and 18. Clearly, 24 divided by 6 is 4 and 18 divided by 6 is 3. So you're working between 3 pi and 4 pi. Where's 3 pi and 4 pi? Which one's 3 pi and 4 pi again? Anyone remember? Where's 3 pi and 4 pi? Remember, odd numbers and even numbers. Where do they sit? This point here. Is that even or odd? Even. And that's the odd. So 4 pi must be here. 3 pi must be there. So if I write it out, 3 pi, 4 pi. But you just told me 23 pi and 6 is clearly closer to 4 pi, because I'm only missing an extra 1 6, isn't it? Whereas that one, I'm missing like 5 6, which is an obtuse angle. So that means I must be in quadrant 4, just through that logic. Yeah, so that's your skill there, to work on that fractional point, to figure out the whole numbers, and that's why we like radians. Radians can get us to work out which region you're in. So now you know you're in quadrant 4. So quadrant 4. So my question is, in this spot here, without knowing ASTC, is the point, at that point there, this very spot, is the y coordinate, because we're looking at sine, is the y coordinate positive or negative? It's negative. Yeah, without memorizing anything. It's just like, yeah, clearly, it's going to be a negative. So I know the answer is negative. If I draw it out, we knew that you only needed an extra pi on 6. Because that's all you're missing. You're just missing an extra pi on 6 to make 4 pi. So you only needed an extra pi on 6. That means the rest here is left over, which is 5 pi on 6. Okay, so this must be 5 pi on 6. So 3 pi to get to 23 pi on 6, we know that was 5 on 6 difference. And then from 23 to 4 was only 1 out of 6 difference. Okay, so out of the two, if you draw a triangle, this is your acute triangle. And we can say that is sine of pi on 6, but negative. Yeah. Okay, so if I drew this triangle out again, just to help you visualize. Here we go. Right angle triangle. This is pi on 6. And we're trying to find this y value. We know the hypotenuse is 1. So according to what we've understood so far, y is equal to sine of pi on 6, or sine of the angle. So sine of pi on 6, but we know it has to be negative, because clearly in quadrant 4 it's going to be negative. So if you want to test your answers to know if you're right, go back to your calculator and test it. So if I go back and I typed in sine of 23 pi over 6, that should give me negative half. But then if I try now, negative sine of pi on 6, I also get negative half. It's the same answer. This is called symmetry properties. Okay, so you're trying to get the angle within an acute angle. Because in the next exercise, which when I see you next, I'm going to teach you to memorize the exact values. That's like your times tables of this exercise. But your skill is to first find what's equivalent. Instead of working with obtuse angles, we need to work with acute angles. And there is 5 special acute angles that you're going to learn in the next lesson, but you need to first understand that. If you get that, that's pretty much it. That allows you to solve x-intercepts. Without this concept, it's harder for you to work out x-intercepts of a circular function. Okay? So that's it for today. It was quite a big chunk, but hopefully it makes sense as I'm going through. It's a picture of a unit circle. The better you understand that picture, the easier it is for you. Okay? All right, I'm going to stop the video there. Got about just under 20 minutes of your time.